Welcome once again to yet another online session on electromagnetic fields. We are discussing the topic of energy and energy density. Let me try to share the presentation to recollect what we have discussed in the previous session. In the previous session, we basically derived the relation of energy in terms of charge, potential, electric field intensity, and electric flux density. These relations are primarily given as W is equal to 1 by 2 summation I from 1 to n QIVI. Here we are talking about energy because of discrete point charges. Similar relation of energy we have when the charge is distributed. Here the relation is in terms of volume charge density, rho v. It is 1 by 2 volume integral of rho v dv. Similarly, we have the relation of energy in terms of electric field intensity. It is 1 by 2 epsilon 0 epsilon r volume integral of magnitude of E bar square dV, and the same relation derived from it in terms of electric flux density dV. In this presentation, we would try to discuss a couple of examples which uses this equations or uses these relations to calculate energy in electrostatic field. Let us start with the first example. The example says that 3-point charges of 1 nanocoulomb, 4 nanocoulomb and 3 nanocoulombs are located at points 000, 001 and 100 respectively. We are supposed to find the energy of this system. Let us say that we have charges Q1, Q2 and Q3 which are given the values 1 nanocoulomb, 4 nanocoulomb and 3 nanocoulombs respectively. What do we know? Because these are point charges, the system that is formed here is basically the system of discrete charges, and hence the relation of work done or energy we can use this. W is equal to 1 by 2 summation I from 1 to n QIVI. Here n would be equal to 3 because in total I have 3 charges. So my relation of energy would be 1 half Q1 V1 plus Q2 V2 plus Q3 V3. Let us recollect that what is the value of V1? V1 is nothing but the total potential at point 1 because of charge Q2 and Q3. Similarly, if I talk about V2, then V2 is the total potential at point 2 because of charge Q1 and Q3, right? So if we try to see what is the relation of the volume, because to calculate this equation, we would have to calculate the value of V1, V2 and V3. So what is the relation of potential because of point charge? The potential because of point charge, say for example, potential at point A because of charge at point B having the value QB is given as QB upon 4 pi epsilon 0 epsilon r RAB, where RAB represents the distance between point A and point B. Point A is the point where I am trying to find the potential, and point B is the point where the charge is located. So the potential is basically given by this relation. So now to calculate potential V1, V2 and V3, we would primarily need the relation of, or we would primarily need the distance between point 1 and point 2, point 1 and point 3, and point 2 and point 3. So these are the values of distances between point 1 and point 2. These are not difficult to calculate because we are given with the coordinate. If I have a point x1, y1, z1, and if I have another point x2, y2 and z2, then distance between two is given as under root of x2 minus x1 square, y2 minus y1 square, z2 minus z1 square. So if I say I am trying to find the distance between point 1 and point 2, which has this coordinate. So it would be 0 minus 0 whole square, 0 minus 0 whole square, 1 minus 1 whole square. So it would basically give me under root of 1, which would be equal to 1 meters. Similarly, distance between 1 and 3, that is 0, 0, 0 and 1, 0, 0 would also be 1. And the distance between 2 and 3 would basically be root 2 meters. I don't think there should be difficulty in calculating this. Once we have calculated this, let us try to calculate value of V1, V2 and V3. So what would be V1? V1 is the potential at point 1 because of the charge Q2 and Q3. So it would be Q2 upon 4 pi epsilon 0 epsilon R R12 at 1 because of 2, and Q3 is 4 pi epsilon 0 epsilon R R13. I can take 1 upon 4 pi epsilon 0 epsilon r as a common term. The value of Q2 is 4 nanocoulomb, so it would, and the distance R12 is 1, so it is 4 into 10 raised to the power minus 9 divided by 1 plus 3 into 10 raised to the power minus 9 divided by 1. This would give me 1 upon 4 pi epsilon 0 epsilon r 7 into 10 raised to the power minus 9. Similarly, I can calculate the value of V2. V2 would primarily because of Q1 and Q3. If I substitute the relations, this is the value that I would get. In the same way, I can calculate V3, which is because of Q1 and Q2. The resultant value would be this. Fine. So now we have the value of V1, V2, V3. So we have to simply substitute these values in this expression and get the value of energy of the system. So if we substitute the values, we have to basically multiply V1 with Q1. Q1 was minus 1 nanocoulombs. This was 4 nanocoulombs and this is 3 nanocoulombs. The result that I would get would primarily be this. If I try to solve it, it results into 13.23 nanojoules. I am sure you would have understood the concept behind this. If you want, you can pause the video here and you can calculate the example by your own, trying to get more clarity about what we have discussed. Fine. If you have comfortably done, let us try to move on to the next example. In the next example, what we are given is that the potential V is given as 2x plus 4y volts and it is present in a free space. We are supposed to find the energy stored in a volume of 1 meter cube which is centered at origin. Let us try to see this in context to the relation of electric field intensity and energy. Right? Because we are supposed to calculate energy, we are not given what is the nature of the charge, we are given with the potential. So if we remember this expression that electric field intensity can be expressed as negative of gradient of V, and we know this relation that energy can be expressed as 1 by 2 epsilon 0 epsilon r volume integral of magnitude of E bar square dV, then we can actually calculate the energy. So what we would have to do the first, we would have to first calculate electric field intensity, calculate the magnitude of it and substitute it in this equation, trying to find the total energy over the given volume. So let us try to do this. We are given with voltages, potential V is equal to 2x plus 4y. E bar, which is equal to the negative of gradient of V, can be given as minus del V by del X AX plus del V by del Y AY plus del V by del Z AZ. This is an easy expression to find because if I try to differentiate this with respect to X, I would get 2 plus 0. If I try to differentiate this, the same expression with respect to Y, I would get 0 plus 4. And if I try to differentiate this with Z, I would get it equal to 0. So continuing with this minus sign, I would get minus 2ax minus 4ay as a result of this computation. Right? So this becomes the value of electric field intensity. If I try to get the magnitude of this would be under root of square of 2 plus square of 4, which is under root of 20. So we have calculated magnitude of E bar. Now we have to substitute this in this relation. So what I would have is W is equal to 1 by 2 epsilon. I have dropped epsilon R because I mentioned that the space is a free space. So I have taken epsilon R to be equal to 1. So 1 by 2 epsilon volume integral of square of magnitude of E bar. So this would give you 20 dV. This 20 is constant. I can take it out. 1 by 2 would give me 10 epsilon 0 integration dV. Now, we actually don't need to calculate this volume because we are given with the total volume, which is 1 meter cube. So I would simply substitute this integration by 1, because when we would calculate this integral, when we are given with some expression of the volume. Here, the total volume itself is given, so this integral is equal to 1. And hence, if we try to calculate, this would result into this expression. So this is my answer. This is nothing but the energy stored in a space which is having this particular potential. One has to understand the approach that we have taken. The examples may change. Here, the potential is given. From potential, we have calculated electric field intensity. Once we get electric field intensity, we can always calculate the magnitude of it. Right? Now, depending upon here, the volume is given directly. So we actually don't have to integrate. But suppose that the volume is not given directly, but it is said, for example, that we have a cube with x ranging from this to this, y ranging from this to this, z ranging from this to this. So if it is a cube, what would I take dv to be? I would take dv to be dx, dy, dz, and then I would have three integration, one ranging for x, another ranging for y, and third ranging for z. So the example can be manipulated with some additional complexity where where we would be required to do integration for calculating the volume. But still, the approach remains same. From potential, we calculate electric field intensity using the relation of gradient. From electric field intensity, we calculate magnitude, and then ultimately we calculate this integral substituted. Right? You can, if required, you can take a pause here. You can go through the example once again, and then once it is clear, we will proceed with the next example. Fine. If it is clear, let us go to the next example. Let us try to find the expression of electrostatic energy stored in parallel plate capacitor. I am sure from our basic study of basic electrical engineering, where we would have calculated energy stored inside a capacitor, we will be at least recollecting that equation. And this is what we are trying to derive here. We are trying to derive expression of electrostatic energy stored in parallel plate capacitor. Let us try to consider a parallel plate capacitor which is charged to potential V, as if I am connecting a source of V volts across a capacitor. So the capacitor is charged to V volts. Let the distance between two plates be small d, and let the surface area of the plate be capital A. These are the standard notations that we use. Now the expression of energy stored in terms of electric field intensity is given as this: 1 by 2 epsilon 0 epsilon r, volume integral of magnitude of E bar square dV. Now, what would be magnitude of electric field intensity here? Let us try to recollect this. This is not difficult to remember. This is not difficult to get. What is, after all, unit of electric field intensity? The unit of electric field intensity is volt per meter. So now, if I know that the potential difference between two plates is V, and the distance between two plates is d, then magnitude of E bar would be V by d. This can also be derived, or this can also be related with or understood in context with the relation of potential and electric field intensity, right? So E bar is equal to V by d, where d is the distance and V is the potential difference between two plates. Now, if I substitute this in the above expression, I would get W is equal to 1 by 2 epsilon 0 epsilon r volume integral of V by d whole square dV. V by d whole square being a constant can be taken out. So I would have basically integration of dV. Now by integration of dV, I am trying to find the volume of this space. Now what is volume of this space? Because this is a parallel plate capacitor, the area of the plates is A, distance between them is D. So the volume would basically be equal to A dot D. What is volume? Length into breadth into height, right? So area of the plates is given, distance between them is d, so the volume would be A into d. So I have the expression of energy stored inside a capacitor as 1 by 2 epsilon 0 epsilon r v by d whole square A dot d. Simplifying this, this would result into 1 by 2 epsilon 0 epsilon r A by d, because from d square this d would get cancelled out, so I would get A by d v square. If we assume, because epsilon 0, epsilon r, area of the plates and distance between the plates all are constants, if we represent this constant by the letter capital C, which we use for capacitance, so C is equal to epsilon 0 epsilon r A by D, then energy is basically 1 half CV square. And this is precisely the relation that we know for energy stored inside a capacitor. I'm sure you would have understood this example as well as other examples that had been discussed in this session. Thank you for joining this session. You can try more examples given as a part of assignment. Thank you for joining this online session. Thank you.